Hello and welcome to the first lecture of fluid mechanics. Today and in the next lecture after this one, we're going to be doing fluid properties. This first one I call fluid properties, and the next one I forget, viscosity and shear or something. But really, it's really all about fluid properties. And the objectives for today's lessons, I'm gonna post these at the beginning of each lecture. At the beginning of this one, we're going to define a fluid. To some extent, you may have a kind of a conceptual idea of what one is. We'll be a little bit more formal about that. We'll talk about the continuum assumption, which is kind of our way of saying that we're working on a branch of mechanics called continuum mechanics. And then we'll define fluid properties and how they vary with respect to temperature and pressure. So this is kind of the main drive of this is, what are these properties and how do they vary? Ultimately, your goal here for this lecture is one that is one of my least favorites, although I'm going to try to spice it up a little bit. But it's one of my least favorites because some of this is a little bit dry. We'll talk about mass and weight and things like that. However, it is critical, absolutely critical, that you get a mental image of what these things are. Okay, so we are going to spend, in some ways, more time on this than necessary. And normally I would quiz you guys on these. But there may not be time for that yet. So we're going to start with the states of matter, which you know well from your high school coursework and really just any coursework. That generally solid, liquid, and gas. And I think it's probably a little more complicated than that, right? We have there's plasma, which I'm not really even qualified to teach about, so I won't even talk about that. And we're going to talk about each of these kind of. Well, let's just kind of dive right in. Okay, so a solid, the visual of a solid, typically we've got a whole bunch of molecules and they're really, really tightly kind of packed in, okay? And I think you can visualize this, and this is definitely the way that I visualize a solid, whatever that solid may be. The molecules are really, really tightly packed. And then we've got a liquid, and they're looser packed, but the key to a liquid is that, while they're pretty close to as packed as a solid, they need a container. So I kind of drew a little container here to hold these molecules, or else they're just not really going to, we're not really going to have them contained. And for a gas, kind of needs to be in a container, but more than that, the container also needs a cap on it, right? So we would need a top on it in order to have our molecules in there. And the molecules are much more widely spaced. Okay, so typically the way we visualize these things is, the difference is the spacing of the molecules. And with a description, basically with solids kind of hold their own shape. Liquids fit the container, excuse my writing. But they also have what is called, they also have what we call a free surface. And so we're going to talk about that a lot. Quote unquote, free surface. And then the gas will fill a closed container. Okay, and that's, I think that this is kind of the way most of us think about these three states of matter. The key here, really, for us, is that this right here. Let me get a slightly different color here. But everything going this way. Okay. These are fluids. Okay, so that's basically gases and liquids. So there are things that they take the shape of their containers. There's a difference between the liquid and the gas, and the main thing is this free surface idea, which I'm going to draw in green right here. So the free surface is right here. Okay, and this is really, really, really important. And typically the way we draw this is we draw a little triangle on top of it, usually with two little lines under it. Usually, it will always either be the triangle or at least one of these two little lines underneath it. I'm usually going to do all of that, but some books or different things will do it different ways. The key about this free surface, and I think that, maybe you can envision this, maybe you can't, but is that it is deformable. Okay, so you could imagine if you threw a rock in here or something, and you threw the rock in here, that this surface would deform and maybe a little wave would form and the wave would propagate to the left and the right, but then eventually that wave would kind of find its way out and we'd be back to where it was. So the surface is free in that it can deform and move around and stuff like that, but ultimately it's going to come back to some sort of homeostasis or something. So it is a surface that is free to move around, but it's going to kind of maintain itself. So that's an important fact. And this little symbol I'm going to draw again and again and again and again 10,000 times. So that is the sign of a free surface. So usually, like if I'm dealing with water, what you'll see is I'll draw, here's the water surface, and then I'll draw a little triangle with 2 little lines under it. And that says this is the free surface. It doesn't have to be water to air or really a liquid to gas. Sometimes you can have 2 liquids on top of each other. Like you could imagine if we had, olive oil. So we had water, and then we had olive oil on top of it. You could imagine another free surface on top of that first free surface. Okay, and those fluids would remain separated because they're immiscible. Okay, so that's really kind of the basic idea of this. I'm going to keep talking about solids and liquids and gases. I'm going to kind of move down. But one of the keys here is this idea of a free surface, and I want you to kind of keep that into your brain. Okay, so we're going to think about a few more things. Okay, so the mobility of the molecules. Okay, so basically, if you're in a solid, okay, the mobility of the molecules is basically low. Okay, we typically think of it as if it has no mobility. Usually, there's such high intermolecular forces between the molecules themselves that we kind of think of this as there's no molecular mobility, although there obviously could still be some. Okay, and as you move to the right, we've got high molecular forces here, comma, but there's still movement. Okay, there's still, but I guess I would call it medium mobility. Okay, and then if we were looking at a gas, basically, the molecules are so spaced that there's low molecular forces. Okay, molecular forces, and of course, so this is like really high mobility. Okay, so basically, as you move from right to left, the molecular forces become less and less important. Okay, and because of that, things become more and more mobile. So the gas is the most mobile, and the liquid is medium mobile, and the solid. Okay, similarly, density here is high. Okay, and you can imagine, well, why is this one dense? Well, it's dense because the molecules are so tightly wound together. Okay, this is going to be medium density, and this is going to be low density. One of the things that I want to point out here, and this is something that I like to think about a lot, is that this is an example, the density of water. If you don't know that symbol, that's okay. We're going to learn it in a second. So this is a parenthesis. The density of water is 1,000 kilograms per cubic meter. Okay, so that's the SI system. The density of air, okay, at sea level, is something like 1.2 kilograms per cubic meter. Okay, so now why do I point this out? The reason that I'm pointing this out is that when I say this is low, and I say that this is medium, really there's no comparison between the two. If you are in a problem and it's got both of these, it's got this number in there somewhere and it's got this number in there somewhere, okay, odds are this one is irrelevant in comparison. Okay, so oftentimes can be ignored. Okay, and we'll talk about that when we get there, but it's just something to be aware of. Notice this is, basically 1/1000th the density of that. So oftentimes gases just don't really matter. Okay, at least from a density standpoint. And so we'll talk about that. Now so you might be saying, well, what about the solids? Well, solids, this is a fluids class, so we probably won't be talking about this all that much. But solids are maybe it's about 10 times the density of water. Okay, so that's depending on what the problem is, It may matter, it may not. Okay, so density of a solid is about 10 times that of water. Okay, so it's just, it's not something that we can rule out right off the bat. Or if we're dealing with solids, we may also have to deal with the liquids. It depends on the problem. So you can't just automatically say I'm going to get rid of it. Okay, so the effect of shear stress. Okay, so this is a stress. So let's imagine I've got a solid like this. Okay, it's a block of wood or something, and I'm going to shear it, meaning I'm going to kind of produce a stress that is kind of lateral like this. Okay, so if we have a shear stress on this object, what's going to happen is this thing is going to want to deform. Okay, so it is basically going to want to go like this. Okay, I think you can probably imagine this. If not, you can just grab a book in your room and you can, push on it the way that I've kind of drawn, and you can imagine that the top is going to go in this case to the right, and the left is going to, and the bottom is going to go to the left, and it's just going to kind of stay there. Okay. Now, if you had a fluid on the other hand, okay, let's suppose you had a parcel of water or something. Okay, it's going to be a little bit harder to do. So let's imagine this is a lake or something. So the lake's kind of got some edges. Okay. And you blow over the top. Okay, because it's kind of harder to push on water, right? You have to think of a way to contain it. Okay, here's our free surface. Okay, and so if you push that way, well, the bottom's going to kind of push back this way. Well, what's going to happen to the water if you push on it like that? Well, it's not going to do like the block of wood did. It's actually going to flow. Okay, so it's going to flow like this. Okay, and you kind of imagine that. I mean, you can imagine, if you've ever looked out over Lake Pontchartrain or any lake that you can imagine, and there's wind blowing over the top. Well, obviously it's going to push the water and it's going to cause it to flow. So the effect of shear stress here is just deformation. Okay, the effect here is flow. Okay, so I'm going to draw a little line right here because that's the line that we kind of talked about earlier, and that's kind of the key here, is that this line exists. Okay, the same thing happens on a gas. It's a little bit harder to imagine how we might do that. So let's imagine we're just somewhere in the atmosphere. So this is the Earth. Okay, and you've kind of got wind blowing this way over the top. Okay, and so it becomes a shear force because there's friction down here at the bed. Okay, and so you can imagine here again, there's going to be a flow. And the flow will probably look something like this. Basically, you're going to have, so if we deform that, if we shear stress that parcel of wind, of air, it is going to flow, okay? And this, of course, is our key right here, okay? And so I'm going to zoom out just a bit, if it will let me. Okay, and we're going to define a fluid right here, because this is the key to what a fluid is, okay? It is a substance that deforms continuously under a shear stress. Okay, and what do I mean by deform continuously? Deform continuously, I prefer, I think this is like a book definition. I don't know where I got this one, but I prefer to think of that as flows. Okay, so if you deform continuously, you're flowing. Okay, so as long as the shear stress is applied, any fluid will continue to flow. Okay, that's just kind of what it is. Okay, so let's go back over here, and I think I have a few more things. Okay, so similar to, sorry, that's my dog. Okay, so we're going to talk about viscosity now, and that will really be the measure of, it'll be the subject matter of the next class. But so viscosity is basically the ability of something to resist that continuous deformation or flow. Okay, so obviously a solid does not continuously deform, so it's not important. Okay, so basically, So, you know, the viscosity of a solid is essentially infinite. It does not flow. Okay, so it's not applicable there. Okay, so the viscosity of a fluid, on the other hand, is high. Okay, so it resists deformation. It resists flow. And we'll talk about kind of what the effect of temperature has on that and things like that. But you can kind of think of this as you know, like a high viscous fluid. So really, really viscous things are things that resist flow. So we can think of, like, if you wanted to compare honey to water. Okay, honey has very high viscosity. Okay, it does not want to flow. Okay, as opposed to air, which has a very low viscosity. You know, and we'll talk about these things more in the next class. Okay, so these two things kind of come together. Okay, a shear stress and viscosity. A shear stress, if you apply a shear stress, the amount of flow you're going to get is going to be determined by how much viscosity there is. Okay, similarly, or in a similar light, we can think about normal stresses. So in a normal stress, if you were to squeeze, so if we have a solid like this, and we were to squeeze it normally like that, axially, okay, you know, there might be a volume change. Okay, so it might squeeze. Okay, so there might be a change in volume. Okay, but and ultimately can cause failure. Okay, so that's interesting. Let's zoom in a little bit so this isn't so far away. Okay, so that's in solids. My chart is getting a little bit messy here. Okay, so if we were to apply a normal force to a liquid, okay, it's almost the same. It's almost the same picture, right? It would need a container, right? And we would need a plunger or something along those lines to squeeze the top. Okay, but as we squeezed it, we could imagine. Well, I've screwed up my colors here, but let's imagine this is after something's been squeezed. Okay, here, after it's been squeezed, we've created a change in volume. Okay, same sort of thing, change in volume. However, no failure. Okay, it's not capable of failing. Okay, which is kind of cool. You know, it could create a flow. Well, no, it can't really, no flow. Can't create a flow. Okay, now on a gas, on the other hand, the last one, it's the same picture as for the liquid, right? I think you can imagine this, like if you were to squeeze this gas, and initially it took up this whole container, okay, after it got squeezed, you can squeeze it way down because there's so few water molecules, okay? And so we're going to get the same thing here, okay? Change of volume, but there's definitely not going to be a failure. And part of that is because this is really highly compressible. Highly compressible, okay? The liquid is not very compressive at all. Usually assumed incompressible. Incompressible, compressible, excuse my English. Okay, usually assumed incompressible. It's not incompressible, but it's assumed incompressible. So we'll talk about that, and the same would be said over here. So this would be difficult to compress. And we'll put some numbers on here in a second. But basically, the modulus of elasticity. So, for example, the modulus of elasticity of water here is about 2.2 times 10 to the 8th pascals, whereas the modulus of like air here is about 1.0 times 10 to the 5th pascals. Okay, so quick errata, I just made that a little cleaner, and this should be to the 9th. Okay, so these are the moduli of elasticity of air and water. And basically it has to do with how much well, we'll talk about it in a second, but basically, this is 4 orders of magnitude, from 5th, 10 to the 5th to 10 to the 9th, 4 orders of magnitude harder to compress a liquid than a solid, or this water versus air. Okay, so it's really impressive, unless the problem is specifically about the compressibility of the fluid, or of a liquid. You're going to assume incompressible. Okay, so I would circle that, unless the question is asking about the modulus of the bulk modulus of elasticity of the liquid. Assume incompressible. Okay, it's going to make your life a lot easier. It's going to make my life a lot easier. The most solids are much more compressible, or even more difficult. So maybe another 2 orders of magnitude here. So this one here might be EV might be order of 10 to the 11th or something pascals. Okay, so another 2 orders of magnitude or something. But regardless, these two are both very difficult to compress. Okay, whereas this gas is very easy to compress, and we'll talk about that. If I can, I'll find some ways to have some problems associated with that. Okay, so what we're going to do now. So this is kind of the idea here. Okay, and now you're kind of like, okay, well, this was a lot. Okay, and I hope that you have a mental image of solids, liquids, gases, and what a fluid is here. And we're going to talk very specifically about the compressibility of the fluid, viscosity. We're going to have a whole class, or at least half of the class is going to be on viscosity, and shear stresses and density and things like that. But what's most important for you to get out of this is, so far, definition of a fluid, okay, the free surface, and that we assume this to be incompressible. Okay, so this will be 1, 2, 3, and then just generally, okay, that liquids and gases are what we're thinking about here. Okay, so you should have a general idea of all of this. So, before an exam, I would recommend you kind of just read over this chart and make sure it all makes sense to you. If you think about these things, a lot of this kind of makes logical sense. And so that's what, ideally, you can kind of ingrain this in your head. Okay, so that should make logical sense. So, all right, so we're going to zoom over here. Okay, and I'm going to start talking about the continuum assumption. Okay, so the continuum assumption is this really cool thing, and it's something that we're not going to talk about a lot. It's just something that it's just how we kind of make sense of the fact that we're dealing with this substance. There's all these molecules, intermolecular forces, and all these things going on, and we just don't want to have to deal with molecules all the time. So here's the way we're going to look at it. Okay, so imagine I have some fluid. Okay, so these little dots and things, these are molecules. Okay, and this is a fluid. Okay, and it's got blue dots that represent its molecules. And what I want you to imagine is that you were to go out there and you're saying to yourself, okay, I want to know the density. Okay, density is represented by this Greek symbol rho, which kind of looks like a balloon flying away or something. Okay, that's how I draw the rho. Okay, and rho is the mass divided by the volume of the object. Okay, and I said to you, okay, we're just going to pick a volume of a certain size. So I'm going to go like right here. I'm going to go really small on the x-axis here, this volume. And I'm just going to pick a volume like right here. Okay, that's a really small volume. Okay, what's my density? Well, my volume is finite, but, so this is finite. But I got 0 for mass. Okay, so maybe I got so I got 0 for my density right there. Okay, now what happens if I increase the size of my volume? So now I'm going to get another data point like right here. Okay, so let's say I double the size or something. Oh, well, I got a molecule in there. It was just one, he was right there, and then I drew over him, right? And you can imagine, well, now we're fairly dense, right? Because my volume is still finite, but I got a particle in here. And so by getting a particle in there, now my density went way up. So maybe I'm up here. Okay, now let's suppose I took an even bigger sample. I went like this. Okay, let's suppose I went just big enough where I didn't get another particle, right? So I'm like right here, and now my volume has dropped my volume got bigger. Okay, so this got bigger, and this stayed the same because I didn't go big enough to get anything, so my density went down. Okay? And you can probably imagine that I could keep doing this. Like if I did a little bit bigger than that, I get 3 more of these. Okay, and so maybe I shoot all the way back up because I got a whole bunch of mass now with just a little bit of additional volume. And so I think, hopefully you can imagine that if I were to keep doing this, this thing is just going to kind of jump around, kind of depending on, obviously, I'm trying to draw this almost randomly, but, I'm not that good at drawing. And as this volume got bigger and bigger, okay, and let's suppose I just kind of make it, whatever. So as the volume gets bigger and bigger, what's going to happen is eventually I'm going to get to a size where every time I double the volume, the mass is going to almost exactly double because I will have gotten big enough where, there's the particles statistically, that it's just highly likely that I'm going to find I'm going to double the number of particles more or less. Okay, so basically this thing is those fluctuations are going to get smaller and smaller and smaller until I hit some size, some volume right here. Okay, some volume. At which point over here, statistically, I could, once I'm in this region, once I'm in a volume larger than a certain volume, it's not really going to matter. I could double the size of the volume and I'm going to double, and the density is going to stay the same because I'm going to double the volume and I'll double the mass. Or I could cut it in half and the same thing would happen. Okay, and so, all of this region right here, okay, this is where we have microscopic variation within a fluid. Okay, so if you are in this scale, okay, that means that the molecules matter. And by molecules, I mean individual molecules matter. Okay, and so that's a key thing. So if you are ever doing fluid mechanics and you end up on really, really, really small scales, you have to start thinking about individual molecules, which kind of stinks. Okay, we don't want to have to do that. Okay, and so the next question was well, geez, I don't really want to do that. When am I going to have to do that? Okay, luckily, these numbers are very, very, very small. Okay, so the volume for water where this happens, okay, is approximately 3.0 times 10 to the negative 23rds cubic meters. Okay, and for air, it's approximately 4.3 times 10 to the minus 14th cubic meters. Okay, so very, 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 very small. Okay, so the key here is that you're almost never going to be in a regime where you're dealing with fluids on that scale. Certainly in this class, it's never going to happen. So basically, this is happening right there at that volume. Okay, so if you are smaller than these scales, then you should start thinking about individual molecules. Okay, not going to happen in this class. This is not a chemistry class, so that's not going to happen here. I will make a note here, however, that there are cases, or maybe not cases, but as you keep going this way, eventually this will start to vary again. Okay, and what we're happening here, when that happens, we are in a volume that we would call, this is macroscopic variation. Macroscopic variation. Okay, and that's where things are changing just because you're moving into different areas of the water or something along those lines. So I'll give you an example. So for example, for a macroscopic variation, I give you the example. This is from my PhD work. So I was working in this area of California where this is California's delta, which most people, even a lot of Californians, don't know exist. But here's some water draining down here. Here's Liberty, quote unquote, Island, which is all flooded. It's a little island called French Island. Okay, and if it will let me zoom in a little bit, which apparently it was not going to let me. And then this right here is this little thing called Cache Slough, which is what I was studying. And so what I did is I went out into Cache Slough. If I kind of zoom in, roughly right in here, if I zoom in, if it will let me, I went out here, and in these locations, right across here, I put a whole bunch of instruments to measure temperature. Okay, I wanted to know what the temperature of this water was. Okay, And basically we were studying it because we were worried about fish and things like that. But if any of you want to talk to me about that, by all means, we can have that conversation. But you can see that at location 1, I put a whole bunch of temperature, what we call thermistors, so basically a thermometer. And I put one at 2, or a bunch at 3, and a bunch at 4, and a bunch at 5. So basically I was trying to get this whole cross section. And if you zoom in, okay, you'll notice that the fluid properties, so this is kind of going across the fluid. So this is the depth right here, depth. Okay, and this is in meters. And this is, I guess, distance from shore. Shore. Okay, this is in meters. Okay, so this is all across this cross section right here. It's kind of like along the surface right over here. Okay, and then these colors represent the temperature, okay, in degrees Celsius. Okay, and of course this is, I made this in 2009 when I wasn't very good at making plots, so I didn't do a good job of labeling it. However, what I think you can see right here, and what I want you to see, is that notice how different the water is, the water temperature. So at the bottom, if you're, okay, these little black things, these are like kind of the bottom of the bed. Okay, the bottom of the in this case, the channel. Okay, and these little these little black crosses, these represent where I had the thermistors in the water. Okay, and you can see this was on November 8th, 2009 at 1 o'clock in the afternoon. And you can see that near the surface, it was about 15.3 degrees. So all this red is about 15.3 degrees. And down near the bottom, 14.5 degrees. Okay, and you can imagine, like some of you guys, most of you guys have swam in a river or something, or a lake or something. And if you're sitting here swimming and you're just kind of minding your own business, okay, your feet get a little bit cold. Okay, and so this would be macroscopic variation of the fluid. Okay, so this is, a meter or so, or 2 meters, or it looks like this is about 3 meters, excuse me. Okay, so obviously this person is really huge. But what's important is that you can, the properties of the fluid change macroscopically. So there is a scale over which they do not vary, which is kind of like that. So this is the macroscopic variation. Okay, let me get a color that is actually going to show up. Okay, so here's a macroscopic variation. Okay, there's microscopic variation. And then there's everything in the middle where there's no variation, Okay. I should note also that this macroscopic variation, it could go down, it could do this, it could do all kinds of things. It's undefined. Okay, it depends on your system. But there's this area in here. And so this region of no variation is what we mean if I say, what is the pressure at this point? Well, that point has a size, and its size is somewhere from, in here. Okay, if I say, what is the density at that point? That's what I mean. It's within that size. Okay, and so within that size, we're not going to worry about the molecules. We're not going to worry about macroscopic variation. We're not going to worry about, individual molecules. We're just going to think that we're going to act as if the fluid is a continuum, as if it has no molecules. It is just the same always and everywhere. Okay, and that's what the continuum assumption is. And so let me see if I can write that out in words for you. Okay, so we would say a fluid can be treated as continuous, even though on a microscopic level it is composed of molecules. Okay, and that is the continuum assumption. Okay, so we're just going to assume that it's a continuous substance, even though really such a thing doesn't truly exist. Okay. So the next of our 3 objectives, so that's 2 of our 3 objectives down for the day. So, we're getting kind of messy here, and we're getting all kinds of different sizes and things. As you'll see, this is kind of a standard for one of my lectures, at least these online lectures. Okay, so we've defined a fluid, so it's something that deforms continuously under shear stress. We've talked about the continuum assumption. Okay, continuum assumption is never really going to show up again, but it is important to understand. Now, again, the only time you're ever going to deal with that is if you get really, really, really small. Okay, so if ever in your working life you end up below, like the scales that you're working at end up below these numbers that we put out over here, then you have to start thinking about individual molecules. Okay, so hopefully, well, I don't know, maybe hopefully it does happen to you. That might be kind of cool. You might be working on something really interesting. Okay, so now we're going to start talking about the fluid properties and how they vary with respect to temperature and pressure. Okay, so that's this third thing, this third objective, fluid properties. Okay, so I'm going to zoom down here. Okay, and before we really get into them, I want to talk about, I'm going to kind of divide these into two main types of fluid properties: extensive and intensive. And really, it's nothing really super exciting about the difference. It's just that, when I'm dealing with a fluid, we're almost always going to be dealing with the intensive property. So the extensive property, I'm not even going to really define these. Your book does, but I'll kind of just kind of start organizing them, and I think hopefully it'll be clear what's going on here. So we'll start with mass, okay? And mass, this is an extensive property. I guess I'll just put a giant E over here, and intensive will be like kind of the intensive version of the same. So mass has a symbol of M, and it is the amount of matter in an object. Okay, so the amount of matter in an object. Okay, and this has units of mass, okay, which will be kilograms or slugs. Okay, some books will use a pound mass right here. We'll use this, pound mass. Okay, I will never use a pound mass, ever, 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 ever use a pound mass. It is a really dumb unit, and we'll talk about that. I'm sure it's going to come up 100 times, especially because some of you guys have had professors that use that, but we're never going to use a pound mass. If I write the word pound, it means pound force. I majorly dislike that unit. The textbook we're using this semester uses pound mass, which is a massively unfortunate, but that's just the way it is. Okay, so then its intensive version is the density. The density, okay? And density has a symbol of rho. Okay, so again, it kind of looks like a little balloon, and is defined as, it's just an equation. So density equals mass divided by volume. Okay. Oh, by the way, note that my capital V's have a little cross on them. That's to denote that it's a volume and not a velocity. I highly recommend that you do something like this. The book this semester uses some kind of weird shaped V. Just you have to be able to distinguish between a lowercase and an uppercase V, because this is fluids, and we will have volumes and velocities. Okay, so the difference between these two obviously is that the density is per unit volume, and so that's the difference between extensive, which I could kind of think of, whoa, that was not what I intended to do. The extensive, which is just the property of some volume of fluid, and the intensive is per unit volume. Okay, so this has units of mass divided by units of length cubed. Okay, so that's mass per volume. And so in the SI system, that's kilograms per cubic meter. And in the English or silly system, depending on what you want to call it, it is slugs per foot cubed. Okay, typically, throughout this class, we're going to use density constantly. Okay, so you really need to kind of have an idea how this works. So one of the important things about density is to know that density is a function of both temperature and pressure. Okay, and so depending on how you're doing it, so typically what will happen is if you're looking for a liquid, okay, and I don't have a copy of your textbook yet, so there will be a chart in your textbook. I mean, I don't know. I'm not 100% sure the copy I have is the copy they're sending me. So anyway, there will be a chart in your book, and it will have the densities of, density can be found is in a chart. Somewhere in that book, in the first two chapters or in the appendix, there's going to be a chart. You need to find it and you need to use it. Okay, that's how we're going to find the density. Or the specific gravity is in a chart. Okay, and from that you can get the density. Okay, so the density of the fluid is in a chart, or the specific gravity of the fluid is in a chart. Okay, if it's a gas, okay, this is a little bit more complicated. you need to use the ideal gas law. Okay, and there are two different versions of the ideal gas law. Okay, and one of them is you guys have probably heard it, PIV-NERT. Okay, where this R right here is the universal gas constant. Okay, the other possibility is that we're going to have what we call the, it's essentially a specific ideal gas law, which is P equals rho times R for an individual gas T. Okay, so the difference between these two R's is this R is universal, and this one is for a specific gas. Okay, and so that is how you're going to get your density. So if I give you a problem and you're sitting there and you go, okay, well, we're dealing with methane. You say, okay, well, methane is a gas. I need the density of methane. So what you'll do is you'll come over here and you'll say, okay, well, methane is a gas, so I'm going to use ideal gas law. Okay, and to do that, you'll need the temperature, you'll need the pressure, and you'll have to get the R for methane. Okay. Now, on the other hand, if, again, this is going to be in a chart somewhere in your book. Okay, unfortunately, I can't tell you where yet since, they haven't sent me that version. We're working on that. And then, on the other hand, for a liquid, there's going to be a chart and you're going to look it up. And usually what happens is these things, for liquid, it's not really pressure dependent. It's really just temperature dependent. So usually what's going to happen is you're going to say, oh, I've got water at 60 degrees Fahrenheit or whatever, and then you go and you look up its density. Okay, so that's how we do densities. Importantly, I want to make note of some very, really the most important density that you'll need to know. And this is density of water is 1,000 kilograms per cubic meter, or it is 1.94 slugs per cubic foot. Okay, so these are the most important ones. Now you'll say, wait, but you said it's a function of temperature, and it is a function of temperature. Okay, so this is for fresh water at 4 degrees C and 1 atmosphere. Okay, so basically, so that's kind of what we're dealing with. This is essentially the maximum density of water. Okay, if I give you nothing else, okay, and you're like, I got to do this problem, I got to work, whatever, I'm running out of time, et cetera, I know we've got density of water, it's got a temperature, I don't have time to look it up. Okay, use these numbers. Okay, these are the key numbers. Okay, a lot of people will remember 1,000 and they will forget 1.94. If I were you, I would commit these to memory. Okay, these are key. You've got to know them. They're super crucial. Okay, so similarly, okay, so that was mass and density. Okay, so mass is just mass and density is mass per volume. So we're going to do the same thing with weight. Okay, and so I'm going to zoom in a little bit. So, we're going to, let's see if we can kind of get where we can still kind of see the pattern here. So we've got weight, okay, which typically has the symbol capital W. Sometimes you'll see F sub G for force of gravity. And weight is defined as the force of gravity on an object, or in this case, on a fluid. Okay, and it is typically defined as weight equals mass times gravity. Now, you guys already know this from your other classes. Let me draw a little line here to kind of separate us here. Okay, and it is measured, okay, in mass length per time squared. Okay, those are its units. Okay, so it is measured either in newtons or pounds force. Okay, again, like in this class, if I say pounds, I mean pounds force. I don't mean pounds mass. Okay, now some of you might say, well, because I will expect you to know that weight is measured in mass length per time squared. You might say, well, how am I going to know how to do that? And here in in green, I'll show you kind of as an aside how you'll know that, is you'll say, oh, okay, well, weight equals mass times gravity. Okay, well, that's cool. So weight is, mass is measured in units of mass. Gravity is usually length, so that's usually feet or meters per second squared, so that's time squared. Okay, boom. That's how we get it, okay? Mass length per time squared. Okay, otherwise, sometimes we'll say that, for example, that a Newton is a kilogram meter per second squared. Okay, so that's mass length per time squared. Okay, similarly, a pound, force naturally, okay, is a slug times foot per second squared. Okay, again, mass length time squared. Okay, so that's where all this comes from. So if you're ever like, I don't know how I'm supposed to memorize that, don't bother memorizing it. Okay, you already know it. It's from weight equals mass times gravity. It's from force equals mass times acceleration. Okay, it's all in there if you know how to read the equation. Okay, so similar to what we did above, where I said, okay, well, there's weight, and then there's so there's mass, and then there's density. So if there's weight, then we need something intensive. Okay, so per unit volume. So weight per volume has a name. Okay, and that name is a specific weight. And this is where things kind of start to get a little bit confusing. And that is defined, so it's a symbol, and it looks like this. Gamma equals weight per volume. Okay? And so that's, and there's another way to do it, which is also that it is rho times g. Okay, and you need to be able to do this both ways, because both these ways are going to show up constantly. Okay, now if we want to know, so basically this is like, how much does a given volume of water weigh, for example? How much does a given volume of air weigh? We might say, well, water weighs a certain amount. So let's talk about its units first. Okay, and so we can imagine we've got weight, which is usually typically measured in newtons or pounds force, okay, divided by volume. So I can take what we had over here, mass length over time squared, so that's the weight, and I'm going to divide that by the volume, which is length cubed, okay? And so I can say that this is measured in units of mass length squared time squared, okay? And depending on what system you're in, that will come to newtons per meter cubed or pounds force. Again, after this lecture, I'm probably going to forget that little f per foot cubed. Okay? Now you might say, okay, but what is specific weight? And here it is. I'll give you an example. This is for water. Okay? Same conditions, fresh water at 4 degrees C in 1 atmosphere. Okay, the gamma of water is 9810 newtons per meter cubed, or the gamma of water, if you're in the silly system, is 62.4 pounds per cubic foot. Okay, and oftentimes I will write this as PCF, pounds per cubic foot. Okay, so that's super critical. Okay, again, you need to memorize these because they're going to show up. Okay, so memorize these, memorize those, they're going to show up. Now, I'm not saying that you should put this on a flashcard and drill it into your brain, but it's just going to show up so often that you will end up memorizing it. And these are critical things. These are like super duper important. One other thing to note is that when your textbook or if you type into Microsoft Word or anything, this symbol, this gamma, okay, it's going to look, I don't think I can draw it, but it's going to look like more like some kind of weird Y. Okay? You should write it like this because that's the easiest way, and that's people recognize that as gamma. This is kind of unrecognizable, but it is just the way that computers draw it. I don't know why. Okay, so just be wary of that. You'll see me kind of, I'll type it out from time to time, and when I do, it's going to come out looking like this. Okay, and not like this. So just be aware of that. Okay, so the last, well, maybe not the last, but one more interesting one from this kind of foursome, And it kind of fits like right in the center here almost, okay, because it's a way to connect these four quantities. Okay, so it's neither intensive or extensive, is the specific gravity. Okay, so this is kind of off by its side. Specific gravity. Okay, now this is confusing because we just had a specific weight. These confuse me, not because I don't know what they are, but just because sometimes my brain kind of spits out one when I mean the other. Okay, so just be aware of that. But the specific gravity of a fluid, okay, so that's going to be S of a fluid, or sometimes it is S dot G, okay, sometimes. And S of F equals the rho of the fluid to the rho of water. Okay, it also, notice I could multiply top and bottom by gravity, and I would get the gamma of the fluid divided by the gamma of the water. Okay, so it is the ratio of the density of the fluid to the density of water. So in other words, if I said something has a specific gravity of 2, that means it's twice as dense as water. If I say it has a specific gravity of a half, that means it's got half the density of water, or it's got half the specific, or it's got half of the specific weight of water. So it's an easy concept, but in applications sometimes we get in the middle of a problem, and it's totally normal of us. It's totally human. It's going to happen to you. Well, maybe it won't happen to you. If it doesn't happen to you, then great. You're better than me. But this is a confusing concept only in light of everything else that we need to learn. Okay, so there's a lot. This course has a lot. It's got a lot of symbols. I'm throwing a lot of them at you right now, and there's more to come. So just be wary. So all the remaining properties that we're going to look at today are all going to be intensive. So I'll kind of keep them on the right-hand side here. If we go back to our original chart, so they're all going to be in this intensive side. So basically per unit volume. So we're going to zoom down here. I'm going to put them under specific gravity, although these won't necessarily have to do with density or specific weight. So we'll start with the bulk modulus. So the bulk modulus of elasticity, I typically tend to use E with a lowercase v. Your textbook uses a K. Either one of them is fine. I will define it mathematically, and it is defined as negative volume divided by the partial derivative of pressure with respect to volume. Okay, now this I find to be remarkably confusing. So what are we even talking about here? So I'm getting some value here, EV, which is, oh my Lord, what does any of this mean? And so I'm going to kind of try to describe this for you, and I'm going to kind of rethink this. So first of all, I don't want to think in terms of partials, so we're going to do it kind of more discretized. So I'm going to make this negative V, or let's say this is approximately equal to negative V, the change in pressure over the change in volume. Okay, and then I'm going to rearrange that to say that that is negative change in pressure over change in volume divided by volume. Okay, so if we look at that right there, I think that maybe we can piece together kind of what this bulk modulus thing, okay, so it approximately equals this, okay, and what it is and what it's all about. So what I'm going to imagine here is, imagine you've got a container, okay, and the container's kind of got a piston on top, okay, and now inside the container, I've got some fluid. Okay, so it could be water, could be a gas, could be whatever it is that you want, so it's in there. And what I'm going to do now is I'm going to increase the pressure on this fluid by driving this piston down. Okay, so if I drive that piston down, what's going to happen here is this fluid is going to shrink. Okay, so now I'm going to do like that. Okay, so I've increased the pressure on the fluid, okay, by driving this piston downwards. And so now all that, that volume has changed. Okay, so the total amount of volume I had went from this much down to this much, okay, by increasing the pressure. Okay, and so hopefully what you can see here is, let's suppose that the volume changed by this much. The initial volume was about this much. Okay, so if I divide this by that, okay, I'm going to get a percentage of the volume that was compressed in this case. Okay, so delta V in this case would be negative. Okay, so maybe we lost, I don't know, half of our volume, right? So we could say then that delta V divided by V is going to be equal to, so if I say, well, delta V divided by V, in this case, is, let's say, negative 0.5, okay? Because I compressed, half of its volume away, okay? So then what this delta P here is, well, that says how much more pressure did I have to add to this system to make that happen? Okay, so let's suppose I added, I don't know, 1 megapascal, okay? So then if I were to plug these numbers in up here, okay, then I plug in the negative, and you see the negative cancels with this negative that's already there, okay, which is nice and convenient. Obviously, that's why they defined it this way. And so then we would say essentially that 1 megapascal is divided by negative 0.5 multiplied by negative 1. And we would say that this quantity for this imaginary problem would be 2 megapascals. Okay? So what this quantity would be doing is it would be telling us how much pressure we need to create essentially 100% change in volume. Okay? So the larger this number is, the more pressure we need to compress something. Okay? So this term, while I haven't defined it in words, this is essentially a mathematical term describing the compressibility of your substance. Okay? So the larger this number is, okay, the harder it is to compress something. Okay? And I think you could see that. So let's imagine we wanted to compress it to a half, to half of its original volume. Well, in order to do that, what if instead of here I needed 10 megapascals? Well, you can imagine that means that I need, that the fluid is less compressible. Okay, so typically, and we talked about this a little bit earlier, but typically for fluids, this number is much, much higher. So unless we are working on a problem that works specifically with the bulk modulus of elasticity, for fluids, we will always assume, okay, so this is always going to be my symbol for assume, incompressible, okay? Unless we are working with a bulk modulus problem, E sub V or K, problem. Okay, so if we're not, if the problem isn't about the compressibility of the fluid, assume it's incompressible, okay? Typically, even gases are considered incompressible unless you start getting speeds that are about a third of the speed of sound. We are not going to deal with compressible flows in this class, so so don't stress about compressibility. We might have a problem here or there where we say, if the bulk modulus is this number and you change the pressure by this much, how much does the volume change? Okay, so that's about the extent of what we'll do there. So the last thing we want to note about this bulk modulus over here, which has grabbed my fingers in a weird way, the last thing we want to note about it is that the denominator here is unitless, okay, which means that the bulk modulus has the same units as pressure. Okay, so depending on your system, so that means it's going to be a pressure, which is a force over an area. Okay, which means, well, forces are usually mass times acceleration, length over time squared, and then this area, 1 over time squared. Okay, so I'm getting into the units again. Okay, so the bulk modulus has units of, mass over length times squared. Okay, so that's all pressures. Okay, and so that's either, depending on what system you're working in, that's either newtons per meter squared, okay, or pounds, again, I'm going to put the F on there for now, but you'll never see it again, inches squared. Now this is totally annoying. Why do they use PSI? So this is a PSI right here, pounds per square inch. Why in the English system do we switch to I for pressure? I don't know, like everything should be feet, but for some reason they do it this way here. So this is a Pascal, and this is a PSI. Okay, so again, this is why this is a dumb system. Okay, note that when you have PSI, easiest thing to do is to convert it to PSF. It's going to make your life a lot easier. We prefer pounds per square foot. It makes the calculations work a lot better. Okay, so the next thing we want to work on, if I scroll down here, is we're going to work on temperature. Okay, I like temperature. Okay, just because, well, my dissertation was on temperature of waters, but also just because this one is easier, and I think most of us have an intuitive idea what this is. So this is the average kinetic energy of the molecules in a fluid. Okay, and I think most of these most of us should have a good intuitive idea what that is. Okay, and in this case, it has units of, typically, if we have to work with it, we'll call it theta, because T is already taken for time, like up here. Okay, and so in this class, we're going to use degrees C or degrees F. I mean, obviously, you could use Rankine or Kelvin, but we're not going to go into that in this class. Okay, so I'm going to skip straight to something else, kind of one of the cool ones, and maybe I'm going to give myself a little space on this one. Okay, so let's get a kind of a clean slate here. Okay, so we will talk about cohesion and adhesion. So cohesion, the prefix here, co, meaning kind of like. So this is basically how much the fluid sticks to itself, and then adhesion is going to be how much it sticks to something else. So we will start, and for this discussion, I'm going to kind of talk about water. So here we have an oxygen and two hydrogens, and typically what happens is, in order for this bond to happen, basically there's an extra electron around the hydrogen, and it kind of floats over towards the oxygen, and there's one over here, and it kind of goes over towards the oxygen, and the oxygen ends up having a -2 charge, which for some reason they call it 2- instead of a -2, whatever. And that leaves hydrogens having kind of a plus charge, and so that's kind of what creates this bond. And so we've got these bonds here, and but what ends up happening because of this is that basically this whole molecule is neutrally charged. However, these molecules that are being shared, they're going to spend a little bit more time over here by this oxygen, and a little bit less time over here by this hydrogen. And so the effect of that is that if there's another molecule floating around, an O and an H and an H, okay, then this is a polar molecule because it's got positive sides to it, and it's got a negative side to it. And so what ends up happening is the positive side of one molecule ends up kind of attracting the negative side of another molecule. So a lot of times I draw that as a dotted line. Okay, so this is a hydrogen bond, okay, and this is in the case of water. Other things will work other ways, but it is because of this, basically, that water adheres to itself. So it kind of wants to stick to itself. So, for example, and I'll try to post a video of this, but you can imagine if any of you guys have ever done this, and you try to get that last little bit of milk into your cup or something, or water, or whatever it might be. And so if this is the top of the water, you're able to get the water surface to kind of stick out just a little bit above the top of the water. And the reason for that is because if we zoom in on these molecules right in here, if I zoom in there, okay, then what's happening is we've got all these molecules, okay, these are all water molecules, and they've all got these hydrogen bonds, and they're kind of pulling on each other. Okay, so now what I want you to imagine is these are all double-sided arrows showing how these molecules are pulling on each other. Obviously, it's not this regular. That's just how I kind of drew it. So it's not in these nice, pretty triangles, but that's just the way I drew it. Okay, and so what you might imagine is that if we consider all of these, that the forces on, say, this one right here, okay, are equal. It's being pulled in this direction and this direction. It's being pulled in all of these on all these directions equally. Now, keep in mind, this is a fluid, and so all these molecules are moving around, so it's changing constantly. However, the ones at the surface, okay, like this one right here, okay, is only being pulled downwards, All the ones at the surface, they don't have any molecules pulling them up. They only have molecules pulling them downwards. So basically, they're pulled downwards until they're, so close to the one below it that, they start to repel because the nuclei are, both negative or, whatever. But they get pulled downwards. And so because of that, what ends up happening is the ones on the surface, they end up kind of crowding together. So if I were to redraw this, you might imagine that the ones at the surface kind of look like this. And then once you get below that, they end up kind of in their regular spacing. Okay? And so you've got this kind of, it's almost like a film on top of the surface of the water, where all of these are pulled together, and they pull together, and so they're all pulling along this surface until you get to the edge of the cup. And so they're able to stick up just a little bit more. Okay, and if you're really careful, you can do things like you could float a paper clip on top of this. If you're really careful about how you do it. I'll try to post a video of a paper clip floating on top. This is why water bugs are able to, I'm not really that great at drawing water bugs, but they're able to kind of walk around in the water. I guess water bugs don't have heads, right? The headless water bugs. I don't know what water bugs are like. So anyway, and so this is what causes a lot of the really cool things. And so this is why raindrops, if you ever really look at a raindrop, they're spherical, is because all the water molecules are pulling towards each other. Okay, it's why if you shake up your oil in vinegar, the vinegar, which is essentially water, is going to, one or the other. Either the oil will form droplets in the vinegar, or the vinegar will form droplets in the oil. And it's the same thing going on again and again. The other really cool thing that you can do about this, and again, I'll post a video about this, but if we imagine, in fact, there'll be several videos. I'll make a list of them in a second. But if you have, so let's suppose you're looking downwards on your cup, like this, okay? And you put a whole bunch of, let's suppose, the typical way you do this, and you can do this at home, this is pretty easy. So you can just sprinkle some pepper on top. This is pretty typical of what happens, okay? And all of these molecules on the surface, they're all pulling on each other in all directions. So the peppers don't move because they're being equally pulled in all directions. However, if you drop the slightest little drop of detergent, okay, so you just go find your dish soap or something and drop it in there, then what the dish soap does, and this is kind of a fancy thing that it does, is that this little hydrogen bond right here that's bonding, so it's basically bonding polar to polar. What happens is when you drop a detergent in there, it's got a polar side, I don't really know what it looks like, and a non-polar side. And what happens is this polar side slides in here and attracts to that, to that one of those poles of the water, and that leaves this non-polar side sticking out. And the non-polar side will not stick to another water. Okay, so if I were to redraw our picture from earlier, we can kind of erase this hydrogen bond, and in its place, we could put this thing, which now it's got a pole on this side, and it's non-polar on the other side. So now it no longer sticks to that water. So in essence, it breaks this bond. Okay, it makes it so these two will no longer stick together. So if you put this soap bubble right in the middle here, then what happens is you have now broken those bonds in the middle, but all around the edges, these are all still pulling on each other. So what will happen is, basically, as soon as you put that drop in there, all of this is just going to slide to the edges, okay? Because they're all still pulling on each other, but in the middle, it's like you've cut that rope. Okay, you imagine tug of war and you cut the middle rope, well, what's going to happen is everybody's going to go to the sides. Okay, and so that's the cohesion. And then I want to talk about adhesion. And adhesion, I don't really know the details of the molecular processes that call adhesion. However, there is kind of an easy way that we think about this as fluid mechanicians. Is we think about, and I guess you could imagine your rain jacket if you have a nice new rain jacket. And so here's your rain jacket surface. Here's another one. This is an old one, or maybe this one's made of jean. This is your jean jacket or something. It's made of cotton or canvas or something. And this one's fancy new. It's got durable water repellent rain jacket. Okay, or you can imagine a lily pad or something like that. And what happens is, in this case, the fluid kind of bubbles up. on that, or what is it, Rain-X that you can put on your windshield? You can put that on your windshield. And what happens is it creates this bubble. It creates this bubble. And you can see that this angle between these two kind of says something about how much the water and the rain jacket adhere. Okay. Similarly, or not similarly, but in an opposite way, if you have a rain jacket, you can imagine that, not a rain jacket, a jean jacket. Okay, it's going to make a shape more like this. Okay, and so this would be kind of the wetting situation, and of course this is why you're going to get all wet, is because the one little drop of water is going to spread as much as it can, get as much wet as humanly possible, and you can see that this angle between here and there, okay, is much different. Okay, and so generally speaking, this angle is kind of going to be how we define how these things work. And so, in your book somewhere, there's going to be a chart, and it's going to tell you something about, what this angle is between certain materials. So, for example, I'm going to combine these two. And what I want to do before I get all the way there is I'm going to take a step back to cohesion, and I want to formalize surface tension kind of in the same way that I had formalized some of the other forces. We're not going to formalize adhesion other than to say that the angle is what's important. Okay, so here we go. Here's the surface tension. Okay, and it's got a symbol like this, sigma. Okay, and I don't really have a words definition for it, but it's this. It's the surface kind of pulling towards each other, and it is defined mathematically. I don't know why this is doing this. There you go. Okay, let's go down here. And we can say that the force due to surface tension is equal to sigma times L. Okay, so that's sigma. This is the surface tension, and this is the length over which it is acting. Okay, so this is a very unusual force. Most of the forces that you deal with are just forces. Every now and then you'll have a pressure, and a pressure is a force per area. This sigma is a force per unit length. Okay, so it is measured in force per length. Okay, so it has, so we can go ahead and figure that out. So it's force per length. Okay, and a force is, again, mass, acceleration, okay, and then time. And then we have the length for the length on the bottom here. And so if we combine all those, it's mass per time squared. Okay, or usually we're either gonna use newtons per meter, or actually I don't even know what the English version is. It's probably pounds per foot, I would assume. It could be pounds per inches. Again, I guess since this is the first lecture, I'll put the F in there, but we're never going to use pounds mass. So just, kind of work that into your brain. Anyway, and so that's the surface tension. And we're going to do a quick problem here because it's one of my favorite things. And so what I'm going to do is I'm going to think about what happens when you combine adhesion and cohesion. Okay, so this is maybe the first problem that we'll do in this class. So if you combine adhesion and cohesion, then we get something called capillarity. Capillarity. Okay? And what I want you to imagine in this case is, let's imagine you have a bowl. Okay? And with some water in it, that's the free surface. And let's imagine that you have a roll of toilet paper. Okay? So whatever, the roll of toilet paper here, and for whatever reason, the roll of toilet paper has gotten into your toilet bowl. Okay, now what happens here? I assume that you guys can imagine that the water is going to climb, okay, up that roll, up that toilet paper. And depending on where the roll is, if the roll's too close, the whole roll's going to get wet. Okay, and that's a tragedy, right? Because then you have to touch disgusting, wet with toilet paper, and nobody wants that. Okay, well, maybe somebody wants that. I don't know who that person is, but it isn't me. All right, so anyway, so that's really horrible. Why is that happening? Okay, and so to get at that, I'm gonna do kind of a simplified version, and this is gonna have to do instead with trees. How does a tree get water up to its leaves. Okay, and so what happens is, and again, I'll show a video of this. This is a 3rd grade experiment, but we can imagine a tube. Okay, so in this case, let's imagine the tubes in a celery. Okay, so a little mini tiny tree. Okay, and we're going to go ahead and I'm going to put that tube into some water, and what's going to happen here? So if this is a cup or something holding water, then what's going to happen is that tube, the water is going to rise in there some amount. Okay, and the question is, how high is it going to rise? Okay, and we're going to just solve for a general relationship for this right now. And so what I want to do here is I want to think about that fluid. Okay, so I'm going to think about this fluid right here, and I'm going to draw a free body diagram. Okay, so the free body diagram of the water. Okay, and I want you to get used to this idea. Okay, in the past we've drawn free body diagrams and other things, but now we're going to draw it of the fluid itself. So the fluid itself looks like this. Okay. Okay, and we now have to identify the forces on it. Okay, and there are a few forces. We've got the weight of the fluid going down. Okay, and then we've got a force coming up here. Okay, so because what's happening here at these edges, so if I look at these edges, what's happening is there's a force all along this top surface. Okay, that's the surface tension force. Okay, and it's pulling upwards like this. F sigma. Okay, let me zoom in on this. Okay, and that F sigma is pulling upwards. Now, what's interesting here, what's important is, well, there's a few things that are important. One, okay, we need to know this angle. Okay, and that angle is a function of, well, what kind of fluid is this? In this case, it's water. And what are the edges of the wall made of? Okay, so we would look that up. Okay, so we would look this up. Okay, and it's a function of the fluid and the wall. Okay, whatever materials those are. Okay, so we would look that up. Okay, so then, I think we're in pretty good shape here, right? If I want to know how far this thing's going to go up, well, let's solve this sucker, right? So we're going to just do some statics. Some of the forces in the z direction. In this class, I'll always use z for vertical equals 0. So we've got F sigma. It's going up at an angle of theta, so we're going to say that's a cosine theta. Okay, and then we're going to subtract the weight, equals 0. Okay, now where in all of this is how high up it goes. Okay, so what we're looking for is this right here. Okay, we want to know this height, h. Okay, so that's, okay, how do we get into that? Well, obviously the higher it goes, the heavier it weighs, so it's going to be in there somewhere. So let's go ahead and let's break these things out. Okay, so F sigma. F sigma, okay, from earlier in the notes, right over here, F sigma is sigma times L. Okay, so we're going to go ahead and go back over here. And I'm going to say sigma times L times the cosine of the theta, okay, minus the weight. Okay, now in fluids class, now typically in other classes, you would take the weight and you would do mass times gravity. Okay, we're not going to do mass times gravity here because I don't know the mass of that water. Okay, so instead, typically the way we do weight in fluids class is we do gamma of the fluid, in this case it's water, okay, times the volume of the water. Because remember, gamma is a specific weight, so it's the weight per volume. So if I take weight per volume and I multiply by volume, I'm going to get weight, okay, equals 0. Okay, so we're getting close, but we have two problems now, which is one of them is the L and the other one is the V. Okay, the L. Okay, so the L is the length over which the fluid is in contact with the tube. Okay, so basically it is occurring here, and it is occurring here, and it is occurring at all of those spots all the way around this tube. Okay, so everywhere where the water is in contact with the wall, that's the length that matters. Okay, that's the length where the surface tension is acting. Okay, so that in this case is the circumference of the circle, so that's 2 pi r, sigma cosine theta minus sigma water. Now the volume, now some of you are going, I don't know the volume of a sphere, but I mean of a cylinder, but you have to know the volume of a cylinder. The volume of any prismatic solid, so is the area of the bottom times the height. Okay, so the area of the bottom is pi r squared, and the height is h, equals 0. So from that, we can solve for h, and we'll get h equals 2 sigma over gamma r. Okay, and this is one of my, oh, I forgot the cosine theta, excuse me, cosine theta. Okay, and this is one of my favorite results. I love this problem. It shows up a lot on tests and quizzes, or well, really tests because there won't be any quizzes. But, and what I typically like to do is I like to change the shapes and make this problem more interesting, because, you know, otherwise what happens is a lot of people like to copy this answer, which is, I don't care if you memorize this. What will be the point of that? Okay, I want to make sure that you understand why this is. So it's important to understand everything in this derivation and how it comes about. But one of the really cool things here is this r, the smaller this r gets, the bigger this h gets. So conceivably, you could soak water up really, really, really long distances if you just make this r small enough. Okay, so one of my favorite problems is, you know, how small does r have to be in order for h to be high enough to get water up into the tops of redwoods, which are, you know, 50 or 100 meters high, you know, which I you know, it's just a problem that I love. Anyway, so let's do the last bit on this. This lecture is getting a little long. We're at an hour 21. We are going to go over, but I think I'll probably give you 2 class periods to look at this one. So the last thing that we have to work on here is a little something called vapor pressure. And vapor pressure is a very weird concept. Okay, so vapor pressure is, well, let's just kind of like, let's dive in and kind of get to a formal definition in a bit. But basically, if we imagine we've got a fluid and it's in a container, a liquid, in this case, it has to be a liquid. And what happens is the molecules within that liquid, the ones that have the highest amount of kinetic energy, are the ones that are going to vaporize. So these guys are going to evaporate if they're at the surface. Okay, right? So they're going to evaporate. And when they do, they're going to go out into the atmosphere, and now this is, let's say this is water, so now these little dots are now water vapor. Before they were liquid water, now they're water vapor. Okay, so every now and then we're going to kind of lose one of those guys or girls, and they're just going to kind of float off, and then they're going to be water vapor, and they're going to go. Okay, now as, you know, if this thing is open to the atmosphere, basically, and you can imagine if you left a cup of water by your bed, you know, you wake up in the morning and some of it has evaporated. Obviously, you know, the warmer it is, the more of it will evaporate, things like that, but generally speaking, you will lose water. Now, if I were to come along here and I was to say, okay, well, that's cool, but what happens if I put a cap on this? Okay, let's suppose we cap this thing. Okay, then what's going to happen is, you know, we're going to keep losing some of these, you know, every so often we're going to lose one of these molecules. And what's going to happen is in here, the pressure is going to slowly increase, okay, because we're getting more molecules in there. Okay, so the more molecules you cram in there, the more the pressure is going to increase. And what will happen eventually is the ones up here that have the least kinetic energy will want to condense back into the fluid. So these guys are going to kind of want to go back this way. Okay, so you know, so some of them are going to want to come back. And eventually what's going to happen is the ones going up, okay, are going to balance the ones going down. So these two are going to balance. Okay, I mean, they don't really equal each other, but they're going to balance. Okay, the point at which they balance is called, you know, the pressure at which they balance is called the vapor pressure. And so sometimes you'll see this called equilibrium. Excuse my squeezing it in there. Equilibrium vapor pressure. Sometimes it's just called the vapor pressure. Okay, and basically what this is at that pressure, basically the volume, the amount of water you have in here will essentially remain constant. Okay, and the pressure up here will remain constant. So it's an equilibrium condition. And what's interesting about this is if you were to come along here and say, you're like, all right, we've got this vapor pressure. Okay, this is no longer changing. So you've got this vapor pressure. What happens then if you like put a little hose right here and you just pull out some of those molecules? Well, then what happens is the pressure up here is now less than the vapor pressure. And what will then happen is you will start to get, the evaporation will overwhelm the condensation. And so you will basically start to boil. Okay, so that would create a situation where there will be some boiling. Okay, now it might be, a very small amount of boiling. It may be a ton of boiling. I'm gonna post this video to this really cool video about the mantis shrimp. I highly recommend you look at it. It's really, really, really cool. The mantis shrimp. There are these researchers at Scripps Institute of Oceanography, and they talked about the mantis shrimp. And the mantis shrimp actually causes this condition by causing really, really low pressures. And so for us, and what the low pressures do is it causes a condition called cavitation. So basically, and this is really where this is gonna matter for us, is that when you get really low pressures within a fluid, sometimes you'll have a fluid, it's up here, and then for some reason there's a region of really, really high velocity. Okay, and if you get high velocity, what happens is the pressure gets really, really low. And if you get really, really low pressures and the pressures inside the fluid drop low enough, then this fluid, which was liquid, becomes a gas. Okay, and that's called cavitation. And when the gas cavitates, what happens is we've got a really, really low, or when the fluid cavitates, we have this region of really, 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 really low pressure, and then it implodes. Okay, and it basically becomes liquid again. And as it does that, this particular implosion, this creates a shock wave. Okay, and that can be very, 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 very bad. So for example, if you've got high velocity, let's suppose you're some of my names, my naval architects, and you've got a propeller, okay, and I don't really know how to draw a propeller, but the propeller is spinning, okay, you've got really, really high velocity. If your propeller is designed poorly, you get lots of these little bubbles, these little cavitation bubbles, and as they implode, these shock waves will consume your blade. Okay, for most of my civils, this is gonna come into account with almost the same diagram. If you have an impeller for a pump, same sort of thing can happen. Okay, and so what we're often going to do in this class is we are going to basically you're going to calculate the pressure at a point. So you'll calculate the pressure, and then you'll compare to the cavitation. To the vapor pressure of that fluid at that temperature. Okay, and so for example, with this textbook, table 2.2 is where you'll look for that. Okay, and I'm already prepared for your questions on that. Anyway, so that's all we got for this. Yeah, so basically, when things cavitate, it is essentially water boiling. Okay, if the pressure is lower than the vapor pressure, things will boil. Okay, so that's about it, and I think that's everything I needed to cover. I'll put some on Moodle. I'll put some videos for you guys, and for anybody on the internet that's looking for videos of things about this that I think are cool. I'm gonna do some mantis shrimp here. I'm also gonna show some guys firing a gun underwater because that creates really, really low pressures, and so you'll get to see these bubbles implode, which is pretty cool. I'm going to post one for, let's see, what else did we cover in this lecture? I don't think I have anything. Oh, there are some really cool surface tension ones, that are kind of like this, these jars with these pepper flakes. They also have some really cool ones that look beautiful because they do it with food coloring. I rather love those. Unfortunately, I would normally show these in class. Yeah, so I'll show you some of these things. I'm not going to show you anything with continuum mechanics or density. Or maybe I'll find something. Anyway, I hope you all are having a good one. That was an hour and a half, so it's a particularly long video. Most of them will not be this long. I'll probably ask you guys to watch this one in a set of 2. So there you go. These are the fluid properties. Oh, last thing. So if we go back to the initial things that we were supposed to do, we're going to define a fluid. Remember, a fluid is anything that deforms. under continuous shear stress. We're going to understand the continuum assumption. Basically, there is a size below which we can no longer think about a fluid as just a fluid. And then this last one right here, define the fluid properties and how they vary with respect to temperature and pressure. So here's this handy dandy chart I made, which it won't let me zoom in on for some reason. And you'll see these are the things we just went over. We haven't gone over all of them, but here's density, specific weights, specific gravity, dynamic viscosity, kinematic. We have not discussed viscosity yet, surface tension, vapor pressure, and bulk modulus of elasticity. And then there are equations for each of them, units, dimensions. And then the way that you read this last bit is it says, so for density, what happens when the temperature goes up? Okay, so that could be read as up to density. Okay, and we say, well, for a gas, the temperature goes down. So think about that as a downwards arrows if the gas is free to expand. And for a liquid, if the temperature goes up, the density goes down. Okay, unfortunately, I couldn't draw arrows in whatever program I created this in. So anyway, so I'm going to post that to Moodle, and I'll try to post it in the comments here if I can do that. But this should help you guys just kind of organize. This right here means beyond the scope of this class, meaning the temperature and pressure effects on the bulk modulus of elasticity I don't really care about. I do expect you guys relatively short order. You should pretty well have this memorized. Okay, normally I give you a quiz. In coronavirus times, I will not give you a quiz on that. Okay, this you have to know. Okay, basically you have to memorize that. Okay, because it should come quickly. If not, what's going to end up happening is it's going to nickel and dime your time, and I'm going to nickel and dime your points. I don't want to nickel and dime your points, and I really don't want to nickel and dime your time because that's usually worth more points than the other ones. Anyway, I hope you're having a good one, and I'll see you next class. Hopefully I get to see you all one of these days. All right, later. Bye. What is that? Shinola.